Hey you, yes, you. Do you want to learn how to shoot hoops like a pro? Where and how hard to strike a football to get into the back of the net? All the secrets lie within this ball. So, you want to learn? Pause. Before we continue, be sure to subscribe to stay tuned to any other concepts I attempt to explain. Play. Hang on, let's rewind that. How about we track the ball and trace its path? Can you tell me anything about this ball? How fast did it get shot? At what angle? How high did it go? How far did it go? These are all aspects that one can calculate. Why? So we can bowl. Let's continue. Let's say a ball is initially at rest on the ground. The ball is then shot, thrown, kicked, whatever, giving it an initial velocity, VO, launched at an angle from the ground of theta. This is all we know, right? No. Remember this bloke? Sir Isaac Newton. What did he introduce? Gravity. Can't forget that. So, this ball will experience gravity, a force which applies a downward acceleration to the ball. Emphasis on the downward. So the ball will experience no acceleration along its horizontal. No acceleration means no change in speed. Good. Let's write this. So, our horizontal acceleration is equal to 0, and our vertical acceleration is equal to negative g. Negative to indicate downwards. From this, we can calculate our ball's velocity in general terms. Initially, our ball has a velocity VO at some angle theta, which we draw as vector. Hang on, what's a vector?
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! Oh yeah!
He's right. So our velocity has a value and a direction. Now, our velocity can be resolved to its axis components. One along the horizontal and one along the vertical, simply by using trig.
Hell no, man. What the
So, draw a right angled triangle and using our angle theta, we can say that cos theta equals our horizontal velocity divided by our velocity. Rearranging to give that our horizontal velocity is our velocity multiplied by cos theta. Once more, sin theta is equal to our vertical velocity divided by our velocity. Therefore, our vertical velocity is equal to our velocity multiplied by sin theta. Beautiful. Back to our accelerations. We know that acceleration is dv by dt. Leaving dv to one side and multiplying our acceleration by dt and taking the integral on both sides, we derive general expressions for our velocities. Looking at our horizontal acceleration, our initial conditions are, at 0 seconds we have an initial horizontal velocity. Then at some time t, our horizontal velocity is some value. Integrating, we get that our horizontal velocity subtract our initial horizontal velocity is equal to 0. Rearranging to give us that our horizontal velocity during flight is our initial horizontal velocity. Why? Don't forget, no horizontal acceleration means no change in speed. You believe me now? Now doing the same along the vertical, our initial conditions are at 0 seconds we have an initial vertical velocity, and at some time t we have a vertical velocity. We get that our vertical velocity take our initial vertical velocity is equal to the negative of gravity multiplied by time. Rearranging to give our vertical velocity during flight is the negative of gravity multiplied by time plus our initial vertical velocity. The same process can be done to get our ball's position at any point in time during flight, and I'll spare you the details. We get that our horizontal position at any point in time is equal to our initial vertical velocity multiplied by time, and our vertical position at any point in time is equal to the negative half multiplied by gravity multiplied by time squared, plus our initial vertical velocity multiplied by time. And now we have all the equations we need to describe and predict our ball's motion. So if I asked you the question, how far did my ball go? All you would need to know is the initial velocity at which the ball was thrown, at what angle and how long it was in the air for. Using our equation for our horizontal position anytime, I would just say, for example, my ball was launched at 60 meters per second at an angle of 30 seconds. And let's say the flight time was 10 seconds. Inputting my values, I'd get that my ball traveled a total of 520 meters. What about total height? My ball would reach its highest point when its vertical velocity is 0, because at the peak of the parabola, the ball's vertical velocity would change directions from upwards to downwards upon descent, meaning for a moment the ball's vertical velocity was 0. Taking our equation for the ball's vertical velocity, all we would need to do is solve for our time t when our vertical velocity is equal to 0. Using our values from before and rearranging, we see that our ball reaches its highest peak after 3.6 seconds of flight. Now take our equation for the ball's vertical position at any point in time, plug in our time, which would result in our ball reaching a maximum height of 46 meters. I just said balls a lot of times there. Balls. What if I wanted to manipulate its path? Say I want the ball to travel further or reach a higher point. What should I do? Let's go back to our equations. We have an equation telling us the ball's horizontal position at any time. So if I'd like to know what would make the ball go further, I'd look at this. There's only one variable that can be changed to increase our range, and that is our initial horizontal velocity. Unless you know a way to control time, please, I'd love to know. Larger initial horizontal velocity means greater range. But trouble occurs as there's two ways to go about this. You can change your launch angle, manipulating the magnitudes of each component respectively, or just increase the ball's initial velocity. We'll get back to that. But for now, how would you increase your maximum height? Our equation for our vertical position shows that the only variable we can increase is our initial vertical velocity. Again, to increase that is to either manipulate the launch angle or increase the initial velocity. Let's look at this angle. Watch as I fire the ball at many different angles. Does anything stand out? If we increase it, our vertical component increases and our horizontal component decreases, and vice versa. But notice, there's a sweet spot. At 45 degrees, both components are equal in magnitude and the ball travelled the furthest. This result is key as it is what will ensure a maximum range, as any angle lower than 45 degrees will result in a smaller initial vertical velocity, resulting in a much shorter air time. Any angle greater than 45 degrees will result in a smaller horizontal velocity, leading to not much distance gained overall. 45 degrees is key. So, if you've made it this far, congrats. Now I can say welcome to Projectile Motion. What you have just seen is a basic introduction, but this branch of physics goes way deeper than this, so enjoy. P.S. Everything I've just said does not apply to the real world, as the effect of air resistance was ignored throughout this video. Thanks for watching.